Hello everyone. Our question for today is the following integral. This integral was proposed by the Indian mathematician Zafar Ahmed in the year 2002. And I'm going to show you how to solve this integral using Feynman's trick of differentiating under the integral sign. So we parameterize this integral, we add some parameter as you will see in a minute, and then we derive with respect to this parameter. So I will call this integral a, and I will add a parameter u here, and I will define the family of integrals I of u, and if we replace u by 1, you will get I of 1 equals to a, and that's our integral. So our goal is to eventually find I of 1. We start with differentiating I with respect to u, so di by du is equal to d by du of this integral. Now, I will interchange the integral sign with this differential operator. Can I do that? The answer is yes. This is a special case of the Leibniz integral rule, which says the following. So the theorem says that if we have a function f of xt, which is continuous in both in x and t, so we should have a function f that is continuous in x and in t, that's one thing, and its partial derivative with respect to x is also continuous in t and in x, of course over some region in the xt plane, and if t is between some a and some b, then we can say that d by dx, the partial derivative with respect to x of the integral from a to b of f of xt dt is equal to the integral from a to b of del by del x f of xt dt. So in this case, we are able to interchange the differential operator and our integral. These conditions are satisfied in our integral, which means we can interchange the integral sign and the differential operator. So now we have to find the derivative of this function. To do that, we have to apply this formula. The derivative of tan inverse of some u of t is u prime of t over 1 plus u squared of t. So we can take out 1 over 1 plus x squared times the square root of 2 plus x squared outside the differential operator because it does not contain any u. So all we have to do is differentiate this part, and that's what we get. So the derivative of the inside with respect to u is the square root of 2 plus x squared, and it's divided by 1 plus whatever you have inside to the power of 2. So we can cancel this factor and this factor, and we can introduce the square here, and we end up with this integral. How would I do this integral? Well, we have to apply partial fractioning. So we can split this fraction into the sum of this and this fraction. I'm going to skip the algebra here for partial fractioning. I will leave it for you as an exercise. And I will just write the answers. So a is 1 over 1 plus u squared. B is 0. C is u squared over 1 plus u squared. And D is 0. And this is what we get, which means the integral of this is equal to the integral of the difference of these two integrals. I will factor 1 over 1 plus u squared here, so di by du will be this expression. So now we have to solve this integral as well as this integral. The formula we're going to use to solve both integrals is this. In the first integral, a is 1. In the second integral, our a is the square root of this. So I will add a square root and square here so that our a becomes very clear. And this is what we get for both integrals. The first one is tan inverse of 1 minus tan inverse of 0. Tan inverse is 1 is pi over 4, and tan inverse of 0 is 0. For the second one, we will end up with tan inverse. Replace x by 1, so we get 1 over the square root of 1 plus 2u squared over u squared, minus tan inverse of 0 is 0. Now this, we can simplify it and write it upside down, so it becomes u over the square root of 1 plus 2u squared. Now let us write it in a nice form. Now our next step is to integrate both sides over u from 1 to plus infinity. Why would we do that? Why would we integrate from 1 to positive infinity? Well, for the left-hand side, this is just I, right? di by du, the integral is I. So it is I of infinity minus I of 1, or more precisely, the limit as u goes to infinity of I of u minus I of 1. And wait a minute, what is I of 1? It is our integral a. So if we can solve both sides, we can create sort of an equation which will solve and end up with the answer for our integral a. So that is the strategy. So our next task is to find I of infinity, as well as solving the right-hand side, which is the difference of two integrals, and then we'll see what we get. Now this is the limit of I of u as u approaches infinity. Here again we can interchange the limit and the integral, and if we replace u by infinity, you get tan inverse of infinity. That is simply pi over 2, and this is how the integral looks like now. Now how would I solve this integral? To answer this question, we should see this little trick. That's the key for solving this integral. I'm going to show that the derivative of this function will be equal to 1 over 1 plus x squared into the square root of 2 plus x squared, which is exactly our integral. And let us work out this derivative. So the derivative of tan inverse of u, as I mentioned in the beginning of this video, is the derivative of the inside over 1 plus the inside squared. And here we simply apply the quotient rule. This is how the quotient rule looks like. U prime v minus uv prime over v squared. The derivative of x is 1. This remains as is. Minus, we copy the x and then derive the denominator, which is this, over v squared, of course, divided by 1 plus this squared, and that's what we get. Now the next steps are just algebra. Here we find the common denominator, and this is what we get. Similarly, we find a common denominator at the bottom, and eventually we get this. If you'd like to read it slowly, you can pause the video here and look at the steps more carefully, and you might be interested in working it out, and of course you will end up with this integral. By doing this, we have solved I of infinity. Let me show you. So I of infinity, or the limit of I as u approaches infinity, which is this integral, of course. Now 1 over this, I can now replace it by the derivative with respect to x of this function, and we have solved the integral. So it is simply this function from 0 to 1. That's it. So I replace 1 minus 0. That's the fundamental theorem of calculus. And we eventually end up with I of infinity is equal to pi squared over 12. Let us now come back to where we stopped. So we stopped at I of infinity minus I of 1 is this. And we also said that I of 1 is our integral a. We just got I of infinity. I will also distribute 1 over 1 plus u squared over these two integrals. So this becomes pi squared over 12. This is our a. And again, here we distribute it as I said. And we end up with this. So what is left here is to calculate this integral minus this integral. The first integral is really easy. We just did a very similar one. That's simply arctan of u. What about this integral? That's what we have to look at more carefully, and I'm gonna call it L just for simplicity. So we end up with pi squared over 12 minus a is equal to this minus L. This integral is pi over 4, you can check it. And this is what we get. I'm going to call this equation star. First of all, we will see how to solve L, and then come back and finally solve for a. Alright, so in order to solve L, we will do the following change of variable. I'm going to let u equal to 1 over t, and we end up with this integral. So this u, and this u are all replaced by 1 over t, as well as this u and this u. And of course, du is what? It is negative 1 over t squared times dt. Let's try to play with this integral a little bit to make it more friendly. There's a lot of terms here. I will start by finding a common denominator here, and t squared. After finding a common denominator, I will take it outside the square root and we'll end up with t. Similarly here, I will do the same thing, and this is the integral we get. These t's cancel out, as well as these. Moreover, this t squared will be cancelled with this. And the integral now looks nicer. It is more simplified. I will add one more step. I'm going to interchange the boundaries here and add a minus. And this minus will be cancelled with this minus. And that is our integral. This is the integral now we have for L. So how would I solve this integral? First of all, I'm going to replace this term by another term. But first of all, I'm going to show you a little trigonometry. We consider it a right triangle. Let's assume that its sides are 1 and a, and let us call its acute angles alpha and theta. So simply tan of theta is equal to the opposite over the adjacent, which is a. So theta, of course, is tan inverse of a. I will also find tan of alpha, that is 1 over a, so alpha is this. Now wait a minute. Theta plus alpha is equal to pi over 2. So that's what we get. And this is a famous identity. For a positive, we always have tan inverse of a plus tan inverse of 1 over a is equal to pi over 2. Now how would I relate this to our integral? I'm going to think of a as the square root of t squared plus 2. So if I place a by the square root of t squared plus 2, then we can replace this integral by pi over 2 minus tan inverse of a. And this is what I mean. So in the next step, we're going to replace this by pi over 2 minus tan inverse of the square root of t squared plus 2, and we will see how it goes. So again, this was our L. Now we replaced it by pi over 2 minus tan inverse of this. Let us now distribute and look at the magic. What do you think we got here? Do you remember this integral? Well, this is I of infinity, the one we did before. What about this? This is a itself. That's the integral we're looking for. So this means we got L is equal I of infinity minus a. What is I of infinity? We just did it. It was pi squared over 12 minus a. So now, if we go back to our relation star, and I mean this, all I have to do is to replace L by pi squared over 12 minus a, and it becomes pretty simple. So this is what I just explained. This is a trivial equation, and this is our a. And here is the answer for this integral. Thank you for watching, and see you in the next video.